by just taking a look at a whole bunch of series and really just thinking critically about which test is going to be the best one to use, right? We learn, I mean, everything up there. This test, like these series, may not include necessarily everything that's I've written up there, and that's is dependent on, like when it comes to telescoping series, for example, generally those are going to look like something I could do in other cases. Now, obviously, if it fails all of these, maybe you could try that even, but generally you're going to be given problems that are going to fall into one of these categories. Okay, so if I am given a series, right? So let's say that I have, n equals 1 to infinity of just an, right? And I want to go through the process of thinking about what I should do, right? I just want to go step by step and just think through this. The book gives this order, which I think is pretty good. I would generally I feel like this one's a pretty easy one to do first or try to think about first, but I'll kind of see what they have for now. So first one. So these numbers here are really given as like these are the order you should try to think about doing. Right? Now you may see one where you're like, oh, well, that's obviously got to be this test. Then you could just skip it. You could just skip straight to it in that case. But if you're given one and you're just not sure, right? This might be helpful to know what to do, right? So, one, if I'm given just the sum of 1 over n to the p power, right? Or if there's a number up there, it's the same thing. I just jump straight to p series. There's no reason why I should use anything else besides p series because that's it. It'll make my life really easy, right? I just have to see what p is, and if it's bigger than 1, it's convergent. If it's less than or equal to 1, then it's divergent. And that's straightforward. Okay. Number 2, if I'm given the sum of AR to the n minus 1 or just AR to the n power, I'm just going to use my geometric series test, right? Which is where I'm going to take that R that's inside, right? And I'm going to say if R is less than 1, then I have a convergent series. If the absolute value of R is because it's going to get small enough, and I can get a value of it. And indeed, that sum is going to be A over 1 minus R. We can find it. We probably don't have to get the sum in this section, but that is going to be the sum. And then if R, the absolute value of R is greater than 1, right, then it's going to be divergent, right? But if I see this form, I should just jump straight to using geometric. Next, number 3, right? We want to ask the question: is this similar to P series or similar to the geometric series? Does it look like one of those two? Right? Well, maybe it would be why use comparison test, one of the comparison tests on it, right? Like instead of if I don't have 1 over n squared, but I have like 1 over n squared plus n, that looks like a P series. So maybe I should just compare it. Let me compare it to the P series. Let me compare it to that one that's P series, where that one I can tell easily, and then just see how this one's related. So I can use either just the plain old comparison test, or I can use the limit comparison test. But either way, that's going to be one of the easier ways to do this. Okay. Number 4, if the limit as is inverse to the infinity of an is not equal to 0, then just use the test for divergence. Say why the test for divergence is divergence. So we're done, right? That an on the inside is just going to straight diverge, so I don't need to do anything else. Okay. Now, number 5 here, right? If I have an alternating series, right, -1 to the n minus 1 or -1 to the n, I should just try to use the alternating series, right? Again, you could argue in some of these cases that you could try to do like the theorem we talked about, absolute convergence in the last section, where if it's absolutely convergent, then it's convergent, right? So if I had like, if I had -1 to the n, but it's over n squared, right? Like, just look at the absolute value of this thing. Just look at the b of n term. Just think about, well, is that convergent or not? And that could give it from there. But we can always safely use the series test as well, where you just have to test the 2 conditions. Okay. 6. So again, I talked about this in the last section, but you don't want to do. You're not going to do ratio and root, right? You're either going to try one or the other, right? You might try to do like ratio test on a problem that should use root test, and then it's not gonna work. So you might have to go back then. But if you did write ratio test successfully and you got one out of it, right? You're not gonna jump to go to root test. That is not the way to go, right? You choose one or the other. The book writes it as 6 and 7. I just did 6, 8, and 6, right? Because again, it depends, right? If I did this branch, I just jumped down to 7. Or if I did this branch, I just jumped down to 7. I don't go backwards. Okay, but in 6a, if I have factorials, if I have just some weird product, or if I have some constants raised to an n power, right, just 2 to the n or 3 to the n, then ratio test is going to be pretty convenient in some of the cases. Now, what if I have a constant raised to the n power, but I also have everything else raised to the n power, right? Well, then it might just be wise to use root test, because that would be easier than trying to take the ratio of those terms. Okay, and then finally, very last one you should go to is integral test. Whereas if I have an equals some function of n, right, where we can evaluate f of x dx, this integral, this improper integral easily, then we can just use the integral test, right? That should just be a last second thing to go, because you can use the other test before that. There's going to be some that are set up clearly to do, and like integral test, right? Like you're not going to have an integral test. It's like, oh, here's this random series. Maybe like it should look pretty particular in a way, right? Like you have a U sub you can do, or it's just, but you should only consider that after you went through it, right? So that's sort of our list. That's kind of what we're going to think through. And for the rest of this time, or maybe only for a fraction of the time, just depending on how we feel about it. Maybe we can end early, aka maybe we can just ask questions or go through some more stuff at the end, but let's just go ahead and do some practice problems here. So any questions for me at the moment before we just take some problems and do it? Hey, that's enough. Okay, so I'm just going to be going through all the even problems here. 11.7, just see how many we can go through and just see if we can figure out the convergence or divergence of these things, right? And you're not going to be given a test. You have to determine that for yourself. So the first one here is n equals 1 to infinity of n minus 1 over n cubed. Okay. So, all right, let's walk through this first. Is this a P series? No. Okay. Is it a geometric series? Do I have a number to a power? Answer is no. I have n to a power, or sorry, a number to the power of n. I don't have that here, right? So, and if you were to try to jump to the test for divergence, its limit would be 0 still. But let's maybe follow the sequence for now, and we'll say, is this similar to a P series, or is it similar to a geometric series? Is it similar to either one of them? What do we think? Yeah, it looks like a P series a little bit, right? Because I mean, we have these numbers here, but you just have like these polynomials, right? So maybe I can compare this to, if I take everything besides the highest degree on each line, let's compare it to n over n cubed, which is what? Yeah, 1 over n squared. Okay, good. So let's think about how these compare, right? Let's look at the numerator first. Is n minus 1 bigger or smaller than n? Smaller. Okay. So the numerator makes this less than this guy at the moment. Okay. Now let's look at the denominator. Right. I have n cubed plus 1. I have n cubed. Which is bigger? N cubed plus 1 or n cubed? N cubed plus 1. Right. But that's in the denominator, so it actually makes it smaller. So both because of the numerator and the denominator, this guy's smaller than this one. So I can actually just use a less than or equal to here. Right? If you try to compare it and you're not sure, you can only use a comparison test, but might as well. We can easily get a sign between there, might as well try it, right? Now tell me about this one. Is this series convergent or divergent? It's convergent. Okay. by what? Why is this one converted? By p series. Okay. So this is convergent, and this one's less than or equal to that one. So is this one? Yeah, it's convergent. Yeah, convergent by comparison. And this is just your plain vanilla comparison test because, I mean, it's really straightforward, right? You have a convergent series, and this is less than a convergent series, so it's convergent. Good. Question? Yes.
Is this, they're equal to, would you have to use the limit comparison test?
Like if you knew that they were just equal to each other. Well, I mean, the only case where you'd have if it was equals if they were the same, series, right? So in that case, I don't know if that choice of comparison would have been good, right? Because it would just be, you would just convert the same series again, right? So you would, I mean, yeah, in the theoretical case, you might try to use limit comparison instead, but you would hope that you could at least see that there's some difference, right? So, yes.
What's the special case for?
What's the special case for? So there's two, basically for the plane comparison test, you have two cases. You have, if you have two series, right? So let's say this is the first one, this is the second one. If the second one's convergent and the first one's smaller than that convergent one, then this one's convergent, right? It's saying I have this object that's small enough to be convergent. And I have this object that's smaller than that small enough object. So that means it's also convergent. Yeah, kind of like, it's just kind of squeezing it, right? It doesn't make sense that the smaller object would be divergent, right? And then the other simple case is where if the second one is divergent and this one's bigger than that one, right? You're saying, okay, well, this one's infinite. So if I have one that's bigger, right, it's just more infinite, it's still divergent. If you have anything besides those two cases, right, you can still use a sort of comparison test, but it has to be the limit comparison. Because if this one's convergent, right, but this one's greater than this convergent one, that doesn't tell me anything, right? So if I say like, oh, this object's small enough, what about this bigger object? Well, I don't know if that bigger object's gonna be small enough or not, right? So the limit comparison test allows me to say whether they compare or not, by like the constant.
That's what you would like to divide that.
Yeah, so I would take n minus 1 over n cubed plus 1 over 1 over n squared and equal.
If you get a number,
Yeah, if you get a number between 0 and infinity, then they either both converge or both diverge. Yeah, and basically just saying, oh, they're only off by a number, right? So if I know the sum of this one, it's basically just this amount off. And since it's a small enough number, or like the number, it's only a constant off. If this one's finite, then this one also is just a number times finite number, right? But in the other case, if you take infinity times 5, it's still infinity, right? So that's the logic. Okay. Any other questions on this one? Or we just go on to the next one? Okay. Cool. Next one. We're gonna have the sum and then equals 1 goes to infinity. Negative 1 to the n times n squared minus 1 over n squared plus 1. Okay. Now, this one we could think about a couple of different ways here, right? Because maybe, maybe it would be worth it to, well, it could still be conversion. Okay, this isn't a p series, right? Because it has a plus 1 on the bottom and there's an n squared minus 1 on the top. It's not a geometric series, even though there's a negative 1 to the end because there's all of this over here, right? It is similar to a p series or geometric series, right? So maybe, we could, start off, maybe let's ignore this negative 1 to the end, right? And I mean, you could try to compare that, but you probably wouldn't. I don't know, it might just be hard to tell, right? Because even if the absolute value of this diverges, that doesn't say anything about the negative one, right? If I were to just take the limit of this piece, right, ignore the negative one. What is that gonna be? 1, right? So if I were just to consider the absolute value of that series, it would be divergent, right? So I can't tell anything at the moment, right? If this limit was something different, then we might be able to work with it, but. So comparison test might work, but I would really want to compare with the negative one there, that's a little odd just because of the sign issue. Test for divergence again, if we have the negative one there, it doesn't work, so we would probably just want to jump right to alternating series, right? Alternating series test, right, I have to pass two things, the two conditions, right? One, the limit has to go to 0 of the b of n term, and 2, each b of n term has to be smaller than the last one, which that might be true in this case, depending, but the limit of that term is 1, right? So what does that tell me about my alternating series? It's divergent. So if I call this 5, right, if that was condition 5, so it's divergent by the alternating series test. So again, you could try to think of this like using some of the steps beforehand. Maybe it would just be easier to jump straight to alternating series test if you have a negative one, right? So one of those you can just kind of like skip the first few, because you'll probably find that those first two might come back up with your discussing. Okay, questions on that one? Okay. Good. Number 6. That is going to be the sum from n equals 1 to infinity of, and we have n to the 2n over 1 plus n to the 3n. Okay, this one's probably pretty obvious as to what you're gonna have to use, but let's just go through the high, kind of. This isn't a p series. We have 3 to the n down there. It's a problem. It's not a geometric series for sure. I can't really compare it to a simple one because I have n powers here. Of not just a number, but n. I can't really take the limit of this thing very easily, so a test for divergence doesn't help. It's not alternating, and then so that brings us to step 6, where there's no factorials. I don't know, plugging in n plus 1 in there might get a little complicated, but we have something, both parts of this are to the n power, right? So what test should I use here to do this one? Root test. Yeah, let's do root test. So I'm going to take the limit as n approaches infinity of the nth root of the absolute value of n to the 2n over 1 plus n, 3n. That absolute value doesn't matter, it's already positive. But what's going to happen when I take the nth root of that thing? Yeah, the n powers cancel at least. Maybe not the n's and the base, but the n powers do. So I'm going to be left with the limit as n approaches infinity of n squared, took out that n, over 1 plus n cubed, because we took out that. Now this one's a lot more manageable to limit, right? So let's think about this one. The highest power I have in the numerator is n squared, and the highest power I have in the denominator is 1 plus n, and then I'm going to have n cubed, right? So I'm going to have an n cubed in that term, right? So what is the limit of this going to be? Do we think? Right? Which is bigger, n squared or n cubed? Yeah, it's gonna be 0. Because n squared is smaller than n cubed, right? N cubed is growing faster than n squared is, right? So I have n squared over n cubed, then n cubed is gonna dominate. So we're just left with 0, alright? Now, why is that significant to us? What does that 0 tell us? It's less than 1, which means what? So we'd say that this is, you could just say convergent, and that, or we might write absolutely convergent. And we'll say by root test. Like that. Okay? Questions? Okay, let's just keep going. We're gonna have. Probably orange this time. Let's do the orange here. Sum from n equals 1 to infinity of -1 to the n minus 1 times n to the 4th over 4 to the n power. Okay. So, is this a p-series? Nope. Wait, 4 to the n. Is this a geometric series? It's still not actually, because we've been to the 4th. So, that doesn't work. If we just have like 1 to the n or 3 to the n here, then that'd be fine. We have n to the 4th power, so it's not a geometric method. Is it similar to a p-series or a geometric series? Well, not quite, because, I mean, if I, like, if it was like a +1 or something off of each, or, you know, the numerator denominator, then it might be. But since I put this into the 4th and 4 to the n, it's a little sketchy to work with, so maybe not. Let's try to avoid comparison. Okay. Test for divergence, we have the -1 and the n minus 1. I don't know. That might be a little weird, but maybe we could try to use alternating tests at least for this at the moment. Okay. So let's think about this, right? Let's take the limit as n approaches infinity of n to the 4th power of 4 to the n. What do we think that limit's going to be? Right, you could try to use L'Hopital's rule a few times to do it. If you wanted to, notice which do you think is going to climb faster, into the 4th or 4 to the n? 4 to the n is going to climb a lot faster, so that means that this limit's going to end up being 0. So that's great. Our first condition satisfied, right? That's good. Okay. Now let's do the second condition, right? This should be really easy. We just have to see if n plus 1 to the 4th over 4 to the n plus 1 is less than n to the 4th over 4 to the n. I don't know. That doesn't, I mean, you know, we could do the derivative stuff we did, you know, yesterday. I don't know. I really don't have time. I'm a little busy, so I don't know if I'm going to do it this way. It's nice that this limit goes to 0, but maybe I'll come back to this. I don't. If I need to, maybe we can talk about it. Let's go to the next step instead. So this definitely both aren't to the n power, but maybe ratio test would be useful as well, right? Because I do have a constant raised to the n power, and I have it's division, but it's still like a product of some kind, right? So let's try ratio test on this thing, right? That's the next one step. I wouldn't want to integrate this for sure. I don't want to jump to integrate that stuff. Let's try to do ratio test. So I want to take the limit as n approaches infinity of the absolute value of, now I'm going to include the -1 here still, so that'd be -1 to the n plus 1 minus 1 times n plus 1 to the 4th power over 4 to the n plus 1 over -1 to the n minus 1 times n to the 4th over 4 to the n. Okay, now that absolute value is going to be really nice because it just takes away that -1 in both cases, right? And so we're going to be left with the limit as n versus infinity of, n plus one to the fourth over four to the n plus one times 4 to the n over n plus 1 to the fourth power. Or, sorry, n to the fourth power. Right, keep change flip on that, the negative one just go away. Okay. Now, is there anything that's gonna cancel here in this case? What do we think? Any sort of cancellation, simplification? Well, what is it? If there's something. What is it? Yeah, we're gonna cancel out a 4 to the n, right? Because this is the same thing as 4 to the n times 4 to the first power. So these guys are gonna cancel each other. So we're gonna be left with the limit, then approaches infinity, of n plus 1 to the fourth power over 4 times n to the fourth power. Okay. Now, if I were to expand this, right, the first term would be n to the fourth power. Right, and then the term here is still into the fourth power. So what is the limit of this thing going to be? Going to be 1/4. Does everyone understand that? Right, the 4 is just there from our cancellation here, and then n plus 1 to the fourth over n to the fourth. As they go towards infinity, that difference is going to be very negligible, so they're going to look the same, right? Or you're just going to get n to the fourth from the top and bottom. And the ratio of the coefficients. Okay. Now, 1/4 is smaller than 1, right? So, what does that tell me about my series? It's convergent. Indeed, it's absolutely convergent by ratio test. Yes. Times 4 to the 1. Yep. Yeah, just because it's 4 to the n plus 1, you can split up that using exponential rules. Questions on that? Okay. If you feel like this step's going to be a pain, just try to move on to the next one. Right. That would be a fun test bonus test problem though, to get one. I force you to do the whole game series. You have to use derivatives and stuff. How to make it up for derivatives. We'll see. Okay. Anyway, any questions on that one? Okay. Let's just keep it going so far. So let's see what we've done conversion. We've actually kind of done P series, alternating series, root test, ratio test. Kind of making our way around here. Good. Only big one really haven't done is, like with our big test is integral test, but it's probably for the best. So let's go ahead and move on to the next one though. Okay, looks like I spoke too soon. Okay. N equals 1 to infinity of n squared e to the negative n cubed. Okay. Now, I still want to run through my list, right? I'll tell you for sure that this looks oddly like, it looks like a very specific example of an integral test problem, which you might be able to see it. If I let this be u, then du would be n squared, and so then I could integrate it and do the indefinite integral there. But let's still try to see if maybe there's a way I could shortcut that, maybe like get to a solution a little easier before doing that. Okay, so P series, no. Geometric series, no. Similar to P series to geometric, no. Test for divergence, yeah. You could do the limit of this one actually, wouldn't be too hard. It would be 0 though, and that doesn't tell you anything. So that it fails the test for divergence. It's not alternating, so we can't do 5. Not everything's to the n power, so that wouldn't be very useful. But maybe we could try a ratio test here for fun. Let's try it out. Let's think through it before we reach the notable, right? So I'm gonna take, so first, I'm gonna rewrite this as n squared over e to the n cubed first. Is that justified? Does that make sense why I did that? Okay. It's just since it's a negative power. Okay. Now if I do ratio test on this one, right? We're gonna have the absolute value, which the absolute value isn't gonna do anything, but I'll keep it anyway. But I'm gonna go ahead, we're gonna have n plus 1 squared over e to the n plus 1 cubed times, and then I just take that and flip it, so I get e to the n cubed over n squared. Okay. Cool. So that's gonna leave me with, I have the limit is n approaches infinity, so we're gonna have n plus 1 squared e to the n cubed over e to the n plus 1 cubed times n squared. Now, what I'll say is that this actually is completely feasible with ratio tests. Okay, and I'll elaborate why. So I can take n plus 1 to the third power, right? We know how to do that, right? It's n cubed plus 1 cubed, right? No. Okay, it is not. It is. If I take n plus 1 to the third power, this is the same thing as n cubed plus 3 times n to the second power times 1 plus 3 times n times 1 squared, and then plus 1 to the third power. For those of you who worked with Pascal's triangle in the past, I know those of you who took Dr. Watt, he would have talked about this. We have the constants 1, 3, 3, 1 on these, which is where I get those from. So if you have a binomial, it's the easiest way to take the cube of it. But that is that cube, so I can apply that here to give me the limit as n approaches infinity. And if you want to as well, I can square this. That would be n squared plus 2n plus 1 e to the n cubed over e to the n cubed. Now, I have e to the n cubed plus 3n squared plus 3n plus 1, right? But if it's though all those exponents are adding, I can just split that up, right? E to the n cubed, e to the 3n squared, e to the 3n, e to the first power, right? Might be easier for me in this case. And then times n squared, right? Now, is there any sort of cancellation that's going to happen in this problem? There's going to be an e to the n cubed that actually cancels out here, right? And then what's going to end up happening is I'm left with the limit as n approaches infinity of, now what I'm going to do is I'm going to take everything with e and kind of separate it out. I'm going to take everything with n and put it together. So I'm going to have 1 over e to the 3n squared, and maybe I'll just go ahead and add these together since I can't really cancel them anymore. 3n squared plus 3n plus 1 times n squared plus 2n plus 1 over n squared. Okay. Can I take the limit of this piece? Right here. I can take the limit of each term individually. What's the limit of this guy going to be? 1. Do I know the limit of this term? 1 over e to the 3n squared plus 3n plus 1. What do we think? If I put infinity into that, I mean, there's a lot of things. There's a lot more terms, but it's just going to be infinity stuff, right? I just have 3 times infinity squared plus 3 times infinity plus 1. So what is the limit of this term? It's 0. So I get 0 times 1, which still gives me 0, right? And this is less than 1, right? We want to see it by ratio test, right? So then that would confirm for sure that was conversion. So if you really didn't want to do integral tests, you could actually do this by ratio. Now. So I'll go and write absolute convergent by ratio test. Now, of course, that's not to say it's the only way to do it, right? If you didn't feel comfortable going through all of that, you could just use integral test because it's very apparent that integral test would be one of the easiest options. So this is sort of my f of n in this case. So I'm going to create an integral from 1 to infinity, take my bounds, and I'm going to replace all the n's here with x. Okay, and so I would want to take. So what would I let u be in this case? Or evaluate the center. Oh, well, actually, before we do this, it's an improper integral, so what's my first step? I have to take it, yeah, so the limit. I've been write some ends now. On the TV, probably been a while since you guys seen so many limits in class, right? I mean, we had to do a lot of all school, but every section generally has sort of limit involved. Okay. Now, if I'm evaluating this integral, what would I let u be in this case? We will be x cubed, and du would be 3x per dx, which I'm going to go ahead and take this 3 and divide it over. So I get du over 3 is x per dx. And I'm going to go ahead and change my bounds, which would just be, I get 1 cubed, which is just 1, and t cubed of, and then we're going to get all the 1/3 out here. We're going to e to the minus u du. What is the integral of e to the minus u? Negative e to the minus u. Well, actually, we have the limit still. Limit as n approaches infinity of 1/3 times negative 1/3 e to the minus u from t, from 1 t cubed, and then we just plug in, right? So we would end up with the limit as t approaches infinity of negative 1/3 e to the negative t cubed plus 1/3 e to the minus 1 power. Okay. Now, this is just a number, so whatever happens with that, that's not a big deal, right? What is the limit of that term going to be? Right, I have negative 1/3 times e to the negative t cubed power. So it has to be 0 because I have a negative on the power, right? So with that negative, I can bring it down to the denominator. Essentially, I can think about that as negative 1/3 times e to the t cubed. But then if I put infinity into that, that's the bottom's just going to go towards infinity, so I get 0. So this ends up, this integral would be just 1/3 e to the negative 1 or 1/3e, right? But really all I need to know is that this converges, right? So this does converge, right? So it's convergent integral, all right? Integral. So what does that tell me about my series? If the integral is convergent, the improper integral converges. What does that tell me about the series? Yeah, it also converges. It's going to be convergent by the integral test. Okay, both work. Both are fine. If you just really didn't want to do integral tests, it's fine. Some people might prefer just to try to do ratio that way. Some people might prefer to do the integral. The integral is not really that hard to evaluate, relatively, right? So, but both ways give us the same answer, right? So it's up to you. Okay. Questions at all for me? Okay. Let's see. So I could keep going, or I can I can stop. Do you want me to do, I mean, I can do a couple more examples, or if you're, feel comfortable, I can. Well, I probably shouldn't ask, unless you guys just want me to. I'll do a couple more. These last couple more. Not as long as this one. This one had like a few interesting little pieces to it though, so. Good to discuss. Okay. So, the first one, looks like it might be difficult, but it's actually really easy. So, we have the sum from n equals. Oh. K, use K this time. Doesn't matter, it's a ducking variable, so it's not a big deal. We have 1 over K times the square root of K squared plus 1. Okay. I'm going to determine if it converges or diverges. So, first thing, is it a P series? Nope. Is it a geometric series? No. Is it similar to a P series or a geometric series? May not look like it, right? But what would happen if this one wasn't here? Right? I would just get the square root of K squared, which is K. So I would just get 1 over K squared. That's definitely a P series, right? So it's only like a little stretch off. It's not like I take off the big term, I just take off the 1, right? So maybe doing a comparison test would be ideal. So we're going to compare this to 1 over K times the square root of K squared, or we just get 1 over K squared. That's the square root of K squared. We get this. Okay. Now, is this plus 1 gonna make the denominator bigger or smaller? Makes the denominator bigger, right? Because K squared plus 1 is bigger than K squared. So that means the whole number, every term is smaller in this case. So it's less than or equal. Makes sense? Okay. Just K squared plus 1 versus square root of K squared. Okay. Do we know the convergence to this one? By what? About the convergence to this one. By what test? Yeah. So it's a big convergence. Yeah, spell it down a little better. Actually, I'll just make it a little worse. I'm gonna do this. Like, I won't make them too. Although this one's a good example. So, I mean, you probably wouldn't mind. Yeah, but I would tell you to use that instead of experimenting. Okay, one more. We're gonna do number 14 here, which is gonna be. Try to use some yellow on here. Well, this is gonna be the sum from n equals 1 infinity of sine of 2n over 1 plus 2 to the n power. This one, we're really gonna have to like, you wanna try to optimize this as much as possible, right? We wanna make our process simple. We don't wanna make this harder for ourselves, we need it to be, right? So the first question is this a P series? No, it's not. Is it a geometric series? No, okay. Is it similar to a geometric series or a P series? Yeah. It is, and the reason we can say that, right, normally you see the sine of 2 in your school, that's a little odd, right? Well, let's think about what sine of 2 does, right? Whenever we had e to the n cubed, whenever we had like 4 to the n, whenever we had n factorial or something, right? That was definitely a game changer, because that thing grew pretty fast, right? So I couldn't really say anything. Sine of 2n doesn't really change very much. I mean, and in terms of the sum, like, sure, I mean, it might change it a tiny bit, but sine of 2n, right? Right, no matter what n is, sine of 2n is always in between -1 and 1, right? So it's always bounded in some way, shape, or form, right? Now, you might look at this and say, well, it looks like it's flipping, so maybe I should just try to use like an alternating series test on this, which, I mean, you might think so, but the issue is, again, is that sine of 2n isn't necessarily -1 to the n, right? I mean, sine, if I put 1 in there, I get sine of 2. Anybody know what sine of 2 is? No, right? It's not, this is not a common number. It's not gonna be -1, right? So alternating, even like, it might act like an alternating, but it's a little sketchy, right? So I don't want to jump to that conclusion, right? But I also feel like, I mean, you could test for divergence again, since that negative, the sign of the 2n doesn't do much, this limit would go to 0, because you basically have something that's going, oh, -1 to 1, cool, and then this one's going, I'm going towards infinity. What are you gonna do? Right? So the limit of that's 0. But then once you kind of get to here, you're just like, well, if I do sine of n plus 1, that's not like that's not really, that's really not going to fit very well, or root test. And I don't think any of you want to try to integrate that. I don't even want to think of it. So we have to come up with something else, essentially. Which again, we were talking about, it's similar because this has a restricted range of numbers, right? It's similar to a geometric series because you have this 2 to the n here, right? So the idea is maybe just like the one we did at the beginning of the last section, let's look at the absolute value of this thing. Okay, right? Because again, if the absolute value of a series converges, then the series itself should converge, right? So let's study that for a moment. So when I take the absolute value, I'm going to get the absolute value of sine of 2n, and then we're going to have just 1 plus 2 to the n itself, right? Because if I take the absolute value of that bottom term, it's still 1 plus 2 to the n. Okay. Now, so I'll go and just leave that series there. We took the absolute value. All right. Okay. Now, who can tell me why is this one helpful when this one won't? Yeah, the top's always going to be positive, right? It's easy for us to compare because it's always positive. So we have a great bound to use, right? When it was going negative and positive, you had to try to cap it on. You would try to think about capping it on both sides, and there was a lot to take in. So this helps us to secure for sure that this, right, this is always positive, and especially what series can I compare this to? Right? If sine of 2n, right, the absolute value, right, sine of 2n itself goes between -1 and 1, so its absolute value goes between what two numbers? 0 and 1. So it's always, so this is always less than or equal to 1, right? So just taking the biggest value in each case, 1, right? This is a little more manageable, right? But we know for sure that this is less than or equal to, right? Because again, sine of 2n absolute value is always less than or equal to 1, right? Maybe I'll write this. Right, so using 1 on that works, okay? Now, I still don't know this one for sure, but this one's very blatantly like very similar to a geometric series, right? So what could I compare this one to? Yeah, just 1 over 2 to the n. Now, do I know which way do I know an inequality there? Which way the inequality would go? Yeah, which way? plus 10, right? Because 1 plus 2 to the n is bigger than 2 to the n, right? So that fraction is gonna be smaller. Okay, so all in all, I could really just compare this extreme left-hand side to this extreme right-hand side. Does this series converge or diverge? Anybody? Tell me if that converges or diverges. So it converges. By how? What is it? Root test, that's true. It would converge by root test. This is also the same thing as just 1/2 raised to the n power though, right? So this is just a geometric series, right? And if I have a geometric series, which does fit the root test, sure. If I have a geometric series, right, as long as the number inside is less than 1, then it's convergent, right? So this one, I'll say converges by geometric series or root test if you want. But if there's like an a in there, it might be you might think a little weird about it. So geometric is the safest one there. And it doesn't matter if there's a number on it or not. Okay, so this one's convergent by the geometric series test, and this one is less than that one. What is this series? Convergent or divergent? Yeah, well, it's just convergent here, right? And this is convergent by what test? Comparison test. But this is the absolute value of this one. So that since this converges, that means this one also has to converge, right? And that's just by that. So again, I might write converges by absolute convergence. Kind of sounds silly, but right? If it's absolutely convergent, right, then that means that it's definitely convergent, right? It just has to follow. There's no way that this one would be divergent. Okay. Now there's cases where this one would be divergent, this one's convergent, not the other way around. Okay. Cool. Questions on that at all? Okay. There is quite a few examples, some good ones to really go over and think about. That's all I have. If anyone has questions, I'm going to stick around as always. If for those of you who were taking the test earlier, you need to take it the final earlier, take it late. Talk to me so we can figure out a day and time for that. And of course, again, if you have questions, otherwise that should be good. So that's on Monday, 11.1 through 11.7. 2 questions in each section. Really just going to be every question asked about something about converging. Okay, just know if it converges or divergent. You might find the sum on some, but no. Board meeting.